Hello, welcome to this class about the polynomial function. We'll discuss mainly three concepts: the behavior in the limit, the intercepts, and their relation with the graph. Just in passing, we'll show how to use some related mathematical theorems and devices. Let's talk about the behavior in the limit, sometimes referred as end behavior. You know that it depends only on the leading monomial. More precisely, it depends on the order of the polynomial. In this case, we have order 3. You know that if the order is odd, since odd exponents distinguish signs, if the exponent is odd, if the order is odd, we will have something like this or something like this. So it will move from very positive towards very negative or from very negative towards very positive. If the order is even, since even exponents don't distinguish signs, it will move from very positive to very positive or from very negative to very negative. And how do we know if it's going to be here or here? The answer is the leading coefficient's sign. In this case, the leading coefficient has negative sign, so we know that things are going to happen in reverse. That's to say, in the left, when the x's are negative, the y is going to be very positive. And in the right, where the x's are positive, the y is going to be very negative. So what we have is a behavior like this. And you can sketch this in the graph. So this is the first hint about how the graph is going to look like. More technically, we denote this way. We say the limit when x tends to infinity of y equals. What I am writing here in green is not a perfect algebraic expression because the infinity is not a number, so we didn't discuss how to operate infinities. But if it helps, you can write it this way. It's going to be infinity to the power of 3 with the minus before. Why infinity to the power of 3? Well, because you are replacing the x with infinity in the leading monomial. Don't forget, this monomial will have an order, that's to say 3, and a leading coefficient, in this case minus 1. If you operate this, infinity to the power of 3 is infinity, and with the minus before, it's going to be negative infinity. In a similar way, you do the same, replacing the x with minus infinity, and what you get is that the limit when the x tends to minus infinity of y must be plus infinity. That's the proper expression of what we expressed here with these arrows. Let's talk about the intercepts. The y-intercept is so easy. You know that it is the value of the function in x equals 0, so what you can call f of 0, and you just have to replace the x with 0 and you get the answer. So in this case, the y-intercept is minus 6. The x-intercepts are the opposite. That's to say, the values of the x in which the y is 0. To get them, you just equal the function to 0 and you solve for x. These values are called usually zeros or roots of the polynomial. So let's do it. We are looking for the solutions of minus x3 plus 2x2 plus 5x minus 6 equals 0. How do we solve this? There isn't a formula for that because this is a third-degree equation. According to the rational root theorem, the only possible rational roots are the dividers of the independent coefficient divided by the dividers of the leading coefficient. This theorem is particularly useful in situations like this, where the leading coefficient is 1, because there is only one divider, the 1, with plus minus, but the sign is treated apart. And at the end, what we get is that the possible rational roots, that are going to be indeed whole roots, are going to be the dividers of the independent coefficient. In this case, the dividers of negative 6, which are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. So here, this is what we write. The 4 possible roots, each one with plus minus. So in total, 8 possible roots. Now, what you can do to try one of them, and to try them one by one, is just plugging them in the equation. That's to say, replacing the x with the root. Or alternatively, and this last option is usually considered easier, you can use what we call the factor theorem. This theorem says that k is a zero of this polynomial p of x if and only if x minus k is a factor of the polynomial. Usually we express it this way. We say if and only if x minus k divides the polynomial. So let's try with x equals 1. Let's try dividing the polynomial by x minus 1. The simplest way of doing this is what we call the synthetic division. So we write it here, we complete the steps, and what we get is that the remainder is 0. So certainly the polynomial is divisible by x minus 1, which means that certainly the 1 is a factor. Let me stress that you don't have to do it this way. You can always plug the 1, and if the result happens to be 0, it's clear that the 1 is a 0, a root of the polynomial. But this is considered to be faster, especially because it's not enough with checking the 1. You need to check many of them. Remember that this method is called synthetic division because here we have what I call the synthetic dividend. Here we have what I call the synthetic divisor. Here we have the synthetic quotient. And here we have the synthetic remainder. We call it synthetic because we don't see all the expression. We don't see the unknowns. We see only the coefficients. You know that you can repeat this again. You can try with another number, maybe the minus 1. You will see that it doesn't work. Maybe the plus 1. You will see that it doesn't work. And when you try with the minus 2, you will see that it works. Here you get a new remainder that's 0. So the x plus 2 really divides the polynomial. And the final conclusion is that this polynomial equals x minus 1, which is the first one that we tried here, x plus 2, which is the second one that we tried, and finally, if you take a look to the quotient, here you have the third one, minus x plus 3. So the three of them are here, and you can equal this to 0, because this is exactly the same as the polynomial, and what we want is the polynomial to be 0. Now, once we have factored the polynomial, we can apply the 0 property. For these three factors multiplied to be 0, one of them at least must be 0. So here we have three options. X minus 1 equals 0, x plus 2 equals 0, and minus x plus 3 equals 0. These are three linear equations. We can solve them so easily, and we are getting 3 zeros or 3 roots. We can use both words. Let me remind you that these are the points in which the polynomial is 0. In other words, these are the x-intercepts, the points in which the graph cuts the x-axis. How does this help us sketching the graph? It's easy. You just locate these points here. So here we have our 3 x-intercepts. Here we have our y-intercept. And now knowing that the graph comes from up down, well, it needs to do something like this.